Hello, we are keeping the ball rolling, made up of myself, Daniel Ayala,
Wyatt Klein,
and Brad Haig.
and welcome to Team 6's presentation for the third stage of our design process for our Battle Frog Rube Goldberg machine. We will begin by explaining how we have progressed to this point in the design phase of our project. We will then discuss updated sections of our first two design phases and how they shaped our third and final design phase. 3D models of each station as well as the entire completed BRG will then be presented and explained. The team will then provide a schematic identifying the chunks that have made up our machine and explain how they are interconnected. We will then display in a time assembly worksheet and cost sheet, which will outline our reasonings behind our assembly and manufacturing cost estimates. Lastly, the team will discuss changes we would implement if given the opportunity in the future.
our team wanted to market our Rube Goldberg machine to middle school students. We wanted this to be entertaining and educational. Ideally, a school would purchase this product to improve SOL test scores in math and science. The team decided to create an S-curve in order to model which type of design we wanted to market to schools, being modular, where it would come pre-built, or bare bones, where there would be extensive assembly required. And from our S-curve, it was evident that a combination of the two was necessary.
The team decided to use the same Gantt chart as our previous one because we were on schedule and completed all of the tasks. The group used the design structure matrix in order to organize the parallel and sequential tasks in order to efficiently complete all of the critical tasks. The team is now in the presentation portion of the project and plan to complete by December 13th as everything has gone to schedule.
The customer profile was created based on the predicted customer needs for the Rube Goldberg machine. We decided to choose a school as it provided a large amount of students to teach and can result in a large amount of sales throughout school systems. This product will appeal to this type of customer because it will gain the attention of students with the hopes of provoking interest in physical concepts through interaction and ultimately provide the school's proficiency readings. The use case was created primarily based on the predicted use of the Rube Goldberg machine by the ideal customer, the school. This provided a basic demonstration of the product's usage, which was selected to be a science fair display within the school. This is done by first assembling the machine and placing it on display where students can watch the machine function and participate in the interactive portions as well. Ideally, the students will leave more interested in physics than previously and have learned about a few basic physical concepts.
A number of customers were selected to be interviewed based on the possibility of using the Rube Goldberg machine. Most of these consisted of schools, where the staff as a whole was interviewed, individual teachers, but also included a parent. Customer statements were gathered and non-repetitive statements were evaluated in order to determine the corresponding customer needs. Then, the customer needs were voted on by the team in order to determine the importance of each to help create the product specifications. Based off the customer statements, target specifications were set, as you can see here. Target specifications and customer needs were then ranked using value for technical importance. These values were used to calculate technical difficulty and priority. Based on all of the data collected, keeping the volume and modularity within the established target specifications would be the most important aspects of the machine.
The team did extensive research in order to determine the ideal price of our Rube Goldberg machine. We came to the conclusion after seeing the competing Goldberg machines ranging in price from $10 to $130. This research helped us define our customer needs because of the reviews customers gave them. The cheapest machines were not as durable, and the most expensive machines were too complex and bulky, to name a few. The group consensus came to $30 being the perfect price in order to rival with the competitors. The team researched intellectual property related to the project in order to gain a better understanding of the patents that could help or hinder our options for station solutions. A total of 5 patents were selected and logged, taking notes of the key features of each, as well as the corresponding limitations and ideas gained from each. The team gathered that we may be limited on the amount of competitive interactions our final proposal contains, the type of construction used for a screw type elevator, the method of folding motion of a trapdoor, as well as the construction method used for creating a launch ramp. However, the team learned that user interaction could be beneficial for entertainment value in the overall final solution, as well as gaining ideas for module screw constructions, ramp constructions, and trapdoor folding methods.
The team began concept generation by brainstorming 10 possible solutions for each of the 3 stations. We decided as a team to have Station 1 bring the ball to a greater height, thus adding potential energy to the system. Station 2 was decided to take advantage of the potential energy of the system in some way, shape, or form. Lastly, the team decided Station 3 could be anything that would wrap up the motion of the ball. Seen here is a snippet of some of the team's ideas for Station 1, in which the ball's potential energy was increased. Once the team developed 10 potential solutions for each station, with 30 total potential solutions, we began concept screening. First, we determined the selection criteria we would use which we were based on our team's established specifications. We then rated each potential solution with pluses, zeros, or minuses based on how well the solution optimized each of the solution criteria. Lastly, the potential solutions were ranked according to their net score, with the positive net score solutions continuing to the next phase of concept selection.
For the potential solutions that were eligible to continue, concept scoring began. We chose 5 more selection criteria based on our team's established customer needs and gave them weights of importance as a team. As you can see, affordability and educational aspects were given the largest weights, as these 2 criteria were decided to be the most important for our Rube Goldberg machine. Each potential solution was then given a rating for each corresponding criteria, which was then multiplied by the criteria's importance. These weights were then summed for each potential solution to determine the best concept to begin developing. As you can see here in our example, the Archimedes screw was determined to be the best possible solution for Station 1. The team followed identical paths to generate, screen, and score each possible solution for each corresponding station. In the end, we determined that the Archimedes screw, dual ramp, and trapdoor tubing were the best possible solutions for Station 1, 2, and 3, respectively. After we determined which solutions would be best to develop, we created CAD models for each, which you can see here.
In order to further the concept selection, the team put together a failure mode and effect analysis. We were concerned about some of the aspects of the design. For instance, the ramp, the ball would sometimes roll off the track and ruin the flow of the machine. In order to fix this, the team decided on using guards in the next iteration. Some of the concerns for the screw was that the ball would become lodged in the screw and that the screw did not align properly with the ramp. In order to fix this, the team wants to increase the height and the diameter of the screw so that the ball will not get stuck and continue throughout the machine. The major concern of the trapdoor was that the opening would not close and the next ball would not fall through without answering a question. In order to fix this problem, the team decided to do further tests on the Arduino and make sure that the trapdoor is functioning. These issues range in severity and will be addressed accordingly. Faults that will delay the process, as those previously mentioned, will be taken care of before aesthetics. We grouped portions of our product together based on function, breaking down our machine into 7 chunks. These chunks are the entrance, increase of potential energy, guided transfer, projectile motion, ball catch, door operation, and the machine exit. Grouping these portions together allows them to be used in future products and designs to accomplish each individual function.
Overall, our product scored predominantly well in our industrial design assessment. In addition to meeting all of the design specifications, our product received high ratings in the categories of educational benefit, quality of user interaction, ease of use, safety, product life, and appropriate use of resources, while receiving moderate scores on product differentiation, quantity of user interaction, storageability, and emotional appeal. A 3D model of our final prototype was created using Inventor in order to assure fit and function, as well as to assure that our design is presented clearly and will be easily modified for new developments.
The team brainstormed on what we would like to change in the future given the opportunity. Station 1 could be improved by making the screw powered entirely by the Arduino, thus removing the hand cranking aspect of it. We also thought making the housing see-through would be a nice improvement, as the user could see the path of the ball as it travels upwards. Station 2 could be made steeper and thinner with multiple possible paths, allowing for multiple parabolas of projectile motion to be seen. Lastly, the team would use a standard servo motor instead of a DC motor, as the Arduino kit that would be included with the project already includes a servo motor, thus reducing the input cost for each machine.
In order to help the team sufficiently determine the cost of the assembly, the team worked together to create an assembly time worksheet. This demonstrated how long the assemblies would take in order to determine how much we would have to pay the workers. The team paired this with 3D testing of the machine in order to determine the accuracy of the worksheet. This was beneficial to the team's economic evaluation because the total assembly was estimated to be under 10 minutes.
The cost of material for each station was calculated and inserted into the table shown. We estimated as a team how long it would take an assembly line worker, paid $20 an hour, to cut each of the materials to the proper dimensions. Once we factored the labor costs in with the material cost for each station, the total manufacturing cost for each machine equated to about $17. Based on cost estimates for production and startup requirements, we have concluded that an initial investment of $10,762.50 will be needed to fund our company. This was determined with a $30 selling price, leading to a quarterly revenue of $20,016, and after taking into account operating costs, a quarterly profit of $9,237.50. This investment will be returned in one lump sum payment at the end of 12 quarters, totaling out to be $15,344.75, which results in a 12% annual return on the investment.
In conclusion, we had planned to create a Rube Goldberg machine directed towards middle school students that will reinforce science and physical concepts, which will be sold to school systems to improve SOL scores. Customer profiles and use cases were used to determine customer needs, and from those we determined our specification. Competitive benchmarking was used to shape the design process, providing insight regarding similar products that are already on the market, while researching related intellectual property helped determine legal design limitations while also providing new ideas. Solutions for each station were selected based on concept screening and concept scoring, accumulating to the total design solution, and failure mode and effects analysis was performed to ensure customer satisfaction. The design solution was divided into chunks of product architecture based on each function of the product in order to allow the reuse of these chunks in future designs. 3D CAD models were created in Inventor to determine preliminary function, followed by testing and refinement of our prototype. In addition, an assembly time worksheet was completed to estimate the cost of our assembly, and this information was utilized in our economic analysis. This analysis was performed taking all known factors into consideration with a few estimates, which determined the initial startup cost to be just under $11,000, which will be paid back at the end of 12 quarters with a 12% annual return on investment. We feel that this presents a great investment value for VTEPS Incorporated to consider, and we look forward to hearing from you regarding this. Thank you.
Thank you.